now let's look at our theorem that tells us when we will have a quadratic form that's positive or negative semi-definite. And to do that, let's take off what we have over here, and then I'm going to write down all 7 of the principal minors for the 3x3 case, and then we'll use those to talk about this theorem about semi-definiteness. Okay, so now we have here, here I've written essentially a kind of generic, arbitrary n by n symmetric matrix, which would be the matrix defining a quadratic form for n variables. But here I've said, let's let n equals 3. So we're talking about a 3-variable problem. We're in R3, so it's a 3x3 symmetric matrix. And here we have all 7 of the principal minors for the n equals 3 case. And I'm going to come back and say more about those in a moment. So here we have our theorem that tells us in general for any n, that tells us a single condition that's both necessary and sufficient for our quadratic form or our matrix to be positive definite, and of course a parallel single condition that's both necessary and sufficient for negative semi-definiteness. And note how that's different from the case of positive definiteness, just like in the n equals 2 case. So everything that we're doing here, just like we said a few moments ago for the positive and negative definite case, everything we're doing is just obviously a generalization of what we did in the n equals 2 case. And so here we have this single condition that's both necessary and sufficient, whereas up here we had a parallel condition that was necessary for a condition on all the principal minors, but in the case of positive or negative definiteness, we had a much weaker, if you like, condition that was sufficient to guarantee positive or negative definiteness. Here we don't have that. Here we have a single condition on all the principal minors, that they have the right sign, that's both necessary and sufficient for our quadratic form to be positive semi-definite, or analogously, negative semi-definite. So let's come over here and see how this theorem works out in the n equals 3 case, and then we'll just quickly say something about the n equals 4 case so we can see how it works in general. So first, let's actually look at these 7 principal minors. Notice that these are the principal minors of order 1. So let's put over here k equals 1, and they involve the row and column 1, the first row and column, the first row and the first column of the whole matrix, which is just A11, the second row and column of the matrix, which is just A22, and the third row and column of the matrix A, which is just A33. And so here I'm just pointing out that the 3 principal minors of order 1 are the ones where the row and column is the first, is row and column 1, or row and column 2, or row and column 3. Here we have all the principal minors of order 2, and here the row and column in a principal minor are the first and second row and column, the first and third row and column, and the second and third row and column. Again, there's 3 of them. And in fact, let's just notice that here there are 3 of these of order 1. Here there are 3 of these of order 2. And then here, of course, we just have row and column 1, 2, and 3, all the rows and columns. And let's say then this is the single principal minor of order 3. So we'll do this again, and there's only 1 of them. Altogether there are 7, and so let me write down here that altogether there are 7. And notice that the number in here Well, actually, it's the number down here. So maybe I should take this off and put it down at the bottom. All that's going on here is that we're covering every single subset of the set 1, 2, and 3 of rows and columns. There's 3, first, second, and third row and column. And so this set here, what we're doing is we're taking every subset of the set 1, 2, 3. Here's all the 3 one-element sets, give me a single row and column. All of the 2-element sets that give me 2 rows and columns, and the single 3-element set that gives me all 3 rows and columns. And of course, the total number of subsets of a 3-element set is 2 to the third, or in general, 2 to the n, right? Well, I don't want to write equals there because this isn't something that's equals, but the set of all subsets of this, there are 2 to the n. But of course, we don't have any principal minor corresponding to no rows and columns, so I have 2 to the n minus 1. In the case when n is 3, that's 8 minus 1, which is 7. So there's 7 principal minors. And so now let's look at the signs. Our theorem says that it's both necessary and sufficient for positive definite quadratic form, or positive definite matrix, that all 3 of these be greater than or equal to 0, all 3 of these be greater than or equal to 0, and that this one be greater than or equal to 0. All the principal minors have got to be non-negative, positive or 0. Now, what about negative definite? Well, for negative definite, things are a little more complicated because we know the principal minors have to alternate in sign. So here I'll use a different color. In fact, maybe up here I'll just put positive definite. And now I'll use a different color here, and we'll say that for negative definite, we have to have the first order principal minors have to be less than or equal to 0. So I'll put that over here in pink. And the second order principal minors have to be greater than or equal to 0. And the third order principal minors have to all be less than or equal to 0, because these all have to be, and let me put negative definite up in this corner up here, and we know these all have to have the sign minus 1. Whoop. Let's get this out of there. These all have to have the sign minus 1 to the k. Right? So here k is 1, so minus 1 to the k is negative, less than or equal to 0. K is 2, minus 1 squared, greater than or equal to 0. K is 3, minus 1 cubed, negative. And so that's the complete story for the n equals 3 case, according to our theorem, covering both positive semi-definite and negative semi-definite, like this. So let's just now quickly see what happens if we have n equals 4. So let me use a different color for that. I'm getting more colors. So let's say n equals 4. And so what happens then? Well, now we have 4 order 1 principal minors because we have a 4th term. And I'll even write that one in here. A 4, 4. I won't write all of the remaining matrices, we'll just say what they are. So we have 3 more of these because we now have to pick up all of the minors, all these determinants, with a first and fourth row, the first and fourth row, the second and fourth row, and the third and fourth row. So now we have 1, 2, 3, 4, 5, 6 principal minors. Up here we have 4 principal minors. Here we now have, in addition to rows 1, 2, and 3, we have 1, 2, and 4, rows and columns, 1, 2, and 4. We have 1, 3, and 4, and we have 2, 3, and 4. So now we have 1, 2, 3, 4 principal minors of order 3. So we have 4 and 6 is 10 and 4 is 14. And then, of course, we have one more. So let's take the 7 off of here. And let's put in our k equals 4. And I'll continue to use orange for this. So let's say k equals 4. We have, and here I'm just going to write the determinant of the matrix A, which is, of course, 4 by 4, and rows and columns are just 1, 2, 3, and 4. So there's one of those, and these add up to 10, 14, 15, which of course is 2 to the 4th is 16 minus 1 is 15. Again, because here we are picking up all of the subsets of the 4-element set 1, 2, 3, 4, consisting of the 4 rows or the 4 columns of our matrix A, of course, except for the empty subset, because there's no principal minor corresponding to that. So again, we get the same conditions for positive definite. We have to have greater than or equal to 0, greater than or equal to 0, same thing here, and the same thing here. So we use the same color here for this, greater than or equal to 0. And then for negative semi-definite, we have still k equals 1, first order principal minors, less than or equal to 0, greater than or equal to 0, less than or equal to 0, and greater than or equal to 0. So again, this covers all of the principal minors, 15 of them, a bunch, for the case n equals 4, and both necessary and sufficient, basically characterizing the negative semi-definite quadratic forms, are having all the principal minors have the right sign, the alternating signs here. And lastly, just let me emphasize here, I guess it should have been obvious as we went along, I don't think I actually mentioned it, that for positive definite, of course, the conditions on the principal minors are that they have to have strict signs. So they'd be greater than 0, less than 0, less than 0. Whereas for negative or positive semi-definite, we have weak inequalities, greater than or equal to 0, less than or equal to 0. So I think that covers all of the, everything that we want to know, everything we're going to need to know about the signs of quadratic forms. That is, when quadratic forms will be positive definite or negative definite or positive semi-definite or negative semi-definite. We now have a way of calculating or figuring out when a quadratic form will have one of these characteristics. And of course, it's exactly the case that a quadratic form will have one and only one of these, or alternatively, it will be indefinite. And so there's only one more thing that we want to do before we finish here, and that is we want to do an example, and in that example we'll see exactly what I just said, that the quadratic form has to have one of these characteristics and only one, or it's indefinite. So we'll take all this off, and then we'll do a brief little example. Okay. Okay, now we've got a little space, and we're going to conclude, finally, this quadratic forms lecture with a little example. So let's have our example be 3 by 3. And so let's say A is the matrix 1, 0, 2. Let's have this be 0, 0, 2, 2, 0, 0. Okay, so mostly zeros. Okay, so that's our 3 by 3 matrix. So our quadratic form is in R3, and we really would not now be able to draw a diagram of the graph because that would be in R4, but we can still find out about it, and we're going to find out about its definiteness properties. So to do that, what do? We look first at the leading principal minors, of which there are only 3. So, in fact, maybe we should also first write out what the quadratic form is. So let's write the quadratic form here. That's going to be x1 squared plus 4 x1 x3 plus 2 x3 squared, if I haven't made a mistake here. That looks right. Okay. And so let's look at our leading principal minors. The smallest order leading principal minor is A11, and that's 1, which is positive. So immediately I know that this quadratic form is not negative definite and it's not negative semi-definite. So I now know that it's either indefinite or positive semi-definite, and it could be, in fact, even positive definite. So let's look at the order 2 principal minor, and what is that? The order 2 leading principal minor, that's 1, 0, 0, 0. That's the leading principal minor here with the first and second rows and columns, and that determinant is clearly 0. Well, that's consistent. It's not consistent with positive definite. So now we know it's not negative, even negative semi-definite, and it's not positive definite. So it's either indefinite or it's positive semi-definite. So the third leading principal minor is the determinant of the whole matrix. And what is that? That is 0. So this is consistent with being positive semi-definite. It's consistent with it, but positive semi-definite actually requires that all the principal minors be greater or equal to 0, not just the leading principal minors. So in the definition over here, in the theorem over here, for now we're focused on semi-definite because we already know that it could not be positive definite or negative definite, and it can't even be negative semi-definite. So we're focused on the question, is it positive semi-definite? And if it's not, it's indefinite. So to be positive semi-definite, it is, it's going to have to be the case that all the principal minors are non-negative. Well, let's look at the remaining principal minors. And of course, here's one principal minor, it's 0, and that's A2, 2, that's 0. It says they have to be non-negative. Well, that's non-negative, so that's okay. And A3, 3 is 2, which is non-negative, so that's good. So there's only 2 principal minors left. I said there were 7 principal minors before, and it looks as if that is exactly the case. We need to look at the principal minors consisting of first row, third row, and corresponding columns. That would be 1, 2, and 2, 2. That is 2 minus 4, which is minus 2. And let's look at the remaining one. That is 0, 0, 0, 2, which has a determinant 0. So that gives us all 7 principal minors, 0, 0, positive, 0, and 0. In fact, it's 1, okay. 0, 0, 0, and minus 2. But positive semi-definite requires that all of the principal minors be positive and, non-negative, positive or 0. That's positive, 0, 0, 0, 0, 0, negative. So this is not positive semi-definite. We already know it's not negative semi-definite. That leaves indefinite. And indefinite means that there are vectors in R3 for which this is positive, and there are other vectors in R3 for which this is negative. So in particular, let's actually just verify directly. I mean, we verified it already using this theorem. But let's verify directly that this is indefinite by finding a vector where it's positive and a vector where it's negative. And of course, we could have done that first and then not even done all this, but the whole point of this was to kind of a little exercise with the theorem. So let's look, for example, at the vector, let's say 1, 0, 1. And what do we have for Q at that vector? We have 1, 0, 1. So this is 1. X2 doesn't show up. So this is 1. This is 1 times 4. This is 1 times 2, so that's 7. So Q of X is 7, which is positive. And then let's look at, let's try 1, 0, and minus 1. Q of X is, let's see, I have 1. I have 1 here, because minus 1 squared is 1. So I have 1 plus 2 is 3. And then here I have 1 times minus 1 is minus 1. I've got minus 4. So I've got 3 minus 4. This is minus 1, which is negative. And so that would be enough all by itself to tell us that this quadratic form is indefinite. Sometimes it's positive. Sometimes it's definite, sometimes it's definite. Sometimes it's positive, sometimes it's negative, and that is all it takes to tell us that it's indefinite. So this is a good little example to see that, and also to see how things work with our semidefiniteness theorem, and actually for the definiteness theorem too, because we can see here that by using the principal minors that this is not positive or negative definite. And that's it for today. That concludes our quadratic forms lecture, and we'll go on from there next time. So see you next time.